Our last video we were looking at this mass spectrometer example. So what's happening is we've got this electric field that's pointing in the negative y direction and a magnetic field that's pointing into the page. So the electric field and the magnetic field are perpendicular to one another, but they're both exerting a force on this charge Q. So we're launching a bunch of particles in the positive x direction. And so the reason we call this a velocity selector is that we have an electric field and a magnetic field that are tuned to certain values so that the net force on this particle in the y direction and the z direction is 0. So that means any objects that have this charge Q are actually going to pass through and maintain their velocity. So any particles that have a different charge, the net force due to the electric field and the magnetic field might not, or this charge might not pass through, so it would accelerate in the y direction. So that's why we call it a velocity selector, right? So any particles that have a certain speed will pass through. So in the example we're given the electric field, we're given the magnetic field, so we're looking for the radius of this path, right? The radius of the circular path. So in the last video, at the end of the last video, we talked about how the magnetic field exerts a force on this particle. Once it gets into this region here, it's no longer experiencing a force due to the electric field, and the charge is going to exert some, or is going to follow some centripetal path, because the force that it experiences is always going to be perpendicular to the velocity vector, so it's going to turn it in this direction. And we'll see that if we changed the sign of this charge, right, let's say this was a negatively charged particle, it would still have the same circular path. It would just go in this direction because the direction of the force due to the magnetic field would be in the opposite direction. So it would still follow a circular path, but it would land over here, right? So my setup for this problem looks like this. So we need the acceleration, right? We need the acceleration in the y direction for this particle to be 0, so it passes through, right? This particle of a certain velocity is going to pass through. So that means the net force in the y direction has to be 0. Now we see that the force due to the electric field is in the negative y direction. Now this is for a positive charge. Positive charge. This problem says that this is a singly charged ion. It's a singly charged ion, but it doesn't say whether it's positive or negative or not. So we'll talk about the differences between a positively charged particle and a negatively charged particle that's passing through this velocity selector. So let's just deal with a positive charge for now. If the electric field is in the negative y direction, it's going to push a positive charge in the negative y direction too. So the electric force is going to be in the negative y direction. So if this was a positive charge, if velocity was in the positive x direction and the magnetic field was into the page, we're going to use the right hand rule. Point the fingers of our right hand in the positive x direction, curl them into the page. My thumb is pointing in the positive y direction. My thumb is pointing up. So the magnetic field is in the positive y, the electric field is in the negative y, but they have to be equal in magnitude and opposite in direction. So the net force in the y direction is 0. That allows this charge to pass through with its velocity in the x direction without touching either of these plates first. So it's not experiencing a force in the y direction. So we set the magnetic force equal to the electric force, and since the magnetic force is at a maximum because the velocity vector and the magnetic field vector are perpendicular to one another, I could just set QVB equal to QE. Now notice the charges cancel out. So even if this was a negative charge, I'd still get this expression for the velocity. V equals E over B. So I use this to find the velocity of the particles that are passing through. What a mass spectrometer does is it sets these two at a certain value so that we get particles of this velocity to pass through. Okay? But we're solving for the velocity first. And the reason we have to solve for the velocity is so we can use this expression, because we're given the mass of the particle, it's singly charged, so we have Q, and we have the magnetic field. So I'm using this to calculate the velocity so I can solve for the radius. So what if we had a negative charge? You see the charges go away, right? This still has to be true for a negatively charged particle. If we go back here and let's say this charge was negative. If this was negatively charged, then the electric field would exert a force on it in the positive y direction. It would attract it to the positive plate that's above it. The magnetic field, if I do the right-hand rule again for a negative charge, the magnetic force is going to flip, so that's going to be in the negative y direction. So a negatively charged particle is going to still experience these forces, but in opposite directions. But we'll still get this expression right here. The magnetic force has to be equal to the electric force. So whether it's positive or negative is irrelevant here. The only difference is what direction it will take when it enters this magnetic field. But again, we're not concerned with that. We're just concerned with calculating the radius of its circular path. So I'm going to use E over B to calculate the velocity. And you might see a problem like a WebAssign later on where they'll start out a similar problem, right? A mass spectrometer problem. They might ask you something like, what does the electric field strength have to be so that particles of a certain velocity pass through? So this is still true, right? That's why we call it our velocity selector, because we can set our E field and B field equal to some value and have only particles with this speed pass through. So watch out for that. You know, you might just have to use this and say, well, they want particles of this speed to come through, and we know what B is. What does E have to be? Okay, so that might be like a WebAssign or, you know, something you see in the future. So we calculate the velocity of the particle passing through, and it's 1 times 10 to the 3 meters per second. So again, we kind of had this discussion about whether the charge was positive or negative. I'm just going to use the magnitude of the charge because we're only concerned with the radius. We're given the mass of the particle. It's singly charged, so I'm going to use 1 unit of fundamental charge, the mass that was given, and now I'm ready to calculate the radius of the circular path. Okay, got the mass, got the velocity from this equation right here. Plug in the charge, plug in the magnetic field, and I get a radius of 1.49 times 10 to the negative 4 meters. So another thing, there's a WebAssign, I believe, where you have 2 different particles, right? So one lands at point P and maybe another one lands at like point P prime or something. And you're calculating the distance between those 2 points. I believe they give you the actual diameter, right? So you have to take this radius, right? I think you have to calculate this radius and double it. Okay, so that's a little pitfall I just want to mention so we can avoid it, because I see that a lot. So just keep in mind that if you're given dimensions or if you solve for the radius, like, you have to double it, okay? Because the distance from where it enters to this point P is actually the diameter, okay? So just something to look out for in that mass spectrometer WebAssign problem. So we've seen that a moving charge experiences a force due to a magnetic field, but we've also seen that from chapter 17 that a current carrying wire is just a wire full of moving charges. So in this diagram I've got a current going in this direction. So that means that the electrons are actually going in the negative y direction. Right? The electrons are going in the negative y direction, but our current isn't. Our conventional current is in the opposite direction, so the positive y. So in this example, I have a wire in a uniform magnetic field that's pointing in the same direction as the current. And so if this is the case, then this current won't experience a force, or this wire won't be displaced at all. But if we change the direction of the magnetic field and we turn it to where it's into the page, what you'll see is the wire bend, right? So if this magnetic field is perpendicular to the current, then the wire will bend because it's the group of charges that are moving due to the current that's going to be experiencing the force. Now I can use the right hand rule here. Okay, I can use the right hand rule here, and I'm going to explain it in two ways. So first I'm going to start with, I'm going to use my right hand and I'm going to point my fingers in the direction of I. So my fingers are pointing up right now in the positive y direction. If I fold my fingers in the direction of the magnetic field, right, so my palm is facing the computer right now, my fingers are up, and I curl them down towards the computer screen, my thumb is pointing to the left, and that's the force, that's the direction of the force that this wire is experiencing. Okay, so that's my cross product. It's actually the cross product between the direction of the current and the magnetic field. Okay, so I like to write it as I cross B because L is a scalar, so I like to write it as the vector I cross B, and I'll show you that in my notes. It just helps me to remember the right hand rule a little better. Now you're saying, okay, you just told me that the charges were moving in the negative y direction, right? Why are you doing this right hand rule like it's the protons moving? Alright, okay, so it's not the protons, right? It's not the positively charged particles moving. It's our free charges, it's negative charges. You're right. So what I'm going to do is I'm going to take my right hand and I'm going to flip it. So my right hand is now, my palm is still facing the computer, but my fingers are actually pointing in the negative y direction, so they're pointing down, right? Like the charges, like the negative charges that are actually moving. I'm still curling my fingers in towards the computer screen, direction of the B field. So now my thumb is pointing in the positive x direction, right? If I do the right hand rule the way I'm supposed to, the negative charges are going down, the magnetic field is into the page, so those charges, or my thumb is pointing in the right direction. But we're dealing with the negative charges, so I have to flip my hand one final time to show where, or the direction of the force that the free charges are actually experiencing. And so this force is actually the force that the electrons, the free electrons, are experiencing due to this B field. Okay, so I still get the same direction of force. It's just I like to use the formula associated with this right hand rule. So I do I cross B and then I get the same direction. Okay, so physically that's what's actually happening. It's the negative charges moving in the negative y direction. The right hand rule tells me that it's experiencing a force in the negative x direction. Okay, but I like to use I cross B. Kind of helps me because we're already on the second right hand rule. We've got two more, so it helps to keep these right hand rules straight. So where do I get this expression from? So if I pick one charge, right, one charge that's moving through this wire, it's experiencing a force due to this magnetic field QV cross B. So that's our old definition of the magnetic force on a single moving charge. But how many charges are in that wire that are experiencing this force? Capital N sub E. Okay, we got to go back to chapter 17 and define the moving charges inside the wire in terms of current, the total number of charges that are passing through. So I've got capital N sub E. A capital N sub E was my charge density times volume, right? So that was lowercase n sub e times a capital V. But the volume of the wire is the cross-sectional area of the wire times its length, right? Maybe it's a cylinder, maybe it's shaped like a rectangular prism, we don't know, but the volume is still the cross-sectional area times the length of the wire. So I'm substituting, so I've got QVB times this many charges. So I've got this force on one charge times all of these charges. So I'm going to take QVB times capital N sub E. But this is the charge density times the volume, which is cross-sectional area times length. So this expression right here, QVB times lowercase n sub e times AL, is the total, or the magnetic force that all of the charges are feeling. Right? Also, we have an expression for the conventional current, which was the electron current times E, and the electron current was the charge density times their drift velocity times the cross-sectional area. So this is I sub E times E. Now the drift velocity is this velocity, right? Because a free charge is moving really, really fast, but a group of charges is moving with the drift velocity V, right? So we can kind of picture them as all having the same drift velocity as they're passing through. So this QVB is dependent upon the group of charges drift velocity. So I see that there's one charged particle, right? The charge of an electron is E, which is what we're going to use for Q, right? These singly charged, these negatively charged particles. So E is Q in this case. V is the drift velocity, and I've got the charge density, and I've got the area. So these four terms, Q, V, charge density, and area, are my conventional current. So I'm going to substitute I in for those two terms, and I get the force is equal to the magnetic field strength times the current times the length of the wire that's in the magnetic field. So F equals BIL, right? F is BIL, but it's a cross product. It's a cross product. So current, I can say, well, it's got a direction, right? It's going to be going this way through the wire or this way through the wire, right? So I can write it as a vector. Magnetic field is a vector. It's the cross product between the current vector and the magnetic field vector. And again, this is how I like to use it because it helps me to use the right hand rule. Fingers in the direction of the current, curl them in the direction of the B field. My thumb is going to be pointing in the direction of the force that the wire experiences. So let's do an example, a magnetic levitation example. So we want this piece of wire to float in the magnetic field. So that means it's not going to be moving, it's going to be stationary, it's going to be suspended in the air. So its velocity is going to be 0 in the y direction, and that means it's got no acceleration in the y direction, which means it's got no force in the y direction. But it's a wire, so it's got a mass, right? So it's got a weight. So there's a gravitational force. So this magnetic field is going to exert a force, and we want it to exert a force in the positive y direction because we want the magnetic force on the wire to cancel out the gravitational force so it floats. So we know the magnitude of the magnetic field, 0.1 Tesla. We know it's into the page. I'm given dimensions of the wire. It's got a diameter of 1 millimeter, and its made out of copper, so maybe I'll have to look up some properties of copper when I'm doing this problem. So it's parallel to the floor, perpendicular to the magnetic field. So it says what current through the wire. We're looking for the current that has to be passing through the wire for the magnetic field, or the force due to the magnetic field, to cancel out the gravitational force. It also says which direction. I think I can do the direction first. So I still have to do the right hand rule, but I gotta kind of do it backwards, because I know that my force has to be in the y direction, or the positive y direction, but I have to find out what direction the current has to be going in. So does the current have to be in the left, the negative x direction, or the positive x direction? So I'm setting up my right hand rule. I want my palm to be facing the computer screen, because it's facing the direction of the magnetic field, because I want to curl my fingers into the page, into the computer screen. But I want my thumb to be pointing in the positive y direction, because that's where the force has to be. So the force has to be in the positive y direction. So that means my palm is facing the computer screen. My thumb is pointing up. My fingers, before I curl them, they're pointing in the positive x direction. So I have to have a current that's going to the right. So I to the right, B into the page, F is in the positive y direction. So I know the current has to be in the positive x direction. So let's find what the magnitude of the force has to be, or the magnitude of the current, excuse me. So I have the magnetic field, 0.1 Tesla. I've got the diameter, right? And the diagram shows it looks like a cylinder. If they don't specify, I usually just assume it's a cylindrical wire, but the picture shows me a cylindrical section of wire. So A is pi r squared, so it's pi times half the diameter squared. In order for the wire to float in the air, the net force has to be equal to 0. So the gravitational force, mg, has to be equal to the magnetic force, BIL. Now I don't have to use the cross product other than finding the direction, right? But the magnetic field and the current are perpendicular to one another. So it's just BIL. I don't have to worry about a sign term or anything like that. So I solve for the current, divide both sides by B, divide both sides by L, and I get this, mg over lb. So I've got a nice expression for current. My problem is, of course, I'm missing two variables. That's not good, right? I really wish I had, like, well, both of them, ideally, right? But I'm actually missing two variables. That makes it impossible for me to calculate the current right now. But these are dimensions that are, or these are properties related to the density of the material, right? So I've got a length of wire and I've got a mass. The density of copper, right, which I looked up, 8.96 times 10 to the 3 kilograms per meters cubed. Density is mass per unit volume. So it's mass per unit volume. It's a cylindrical piece of wire. The volume is the cross-sectional area of the wire times the length. Now I was given the diameter, so I can calculate this area. So I'm not actually finding the mass of this wire or the length of this wire, but I'm finding what we refer to as the linear density, right? The linear density, mass per unit length. So I'm looking for a ratio m over L, and I can solve this here. I have the density, right? Mass per length is density times the area. So I can calculate the area, pi times half the diameter squared. I looked up the density, so I can calculate the mass per length ratio, the linear density. And so I'm going to substitute that value in for m over L. Alright, so if you get to a point where you're stuck and it has, you know, mass and maybe some physical dimensions concerning the wire, look at density. Right? Look at the definition of density. That's information that we can, we can find the value. If you're given the type of wire, right, you can look up its density and you could at least, you're not solving for these individual values, but you can at least look for some ratio that's missing and use that to solve for that ratio. So I'm getting a mass to length ratio of 7 times 10 to the negative 3 kilograms per meter. So I'm going to substitute this in for m over L. I know what G is, and I know what the magnetic field is. Right? So I've got m over L now. I've got the acceleration due to gravity, and I was given the magnetic field strength. So the current is 0.68 amps. So that's the magnitude of the current that has to pass through the wire for the magnetic force to cancel out with the gravitational force. And I did this first. I solved for the direction first. I needed a force in the positive y direction. The magnetic field was into the page, the negative z direction. So my current has to be passing through in the positive x direction. I cross B gives me a magnetic force in the positive y direction. Sorry, these are a little light. I tried to darken them up as best I can. If you have access to a printer and you can print them out there, they come out a little bit nicer. So I've got a set of wires, and it doesn't really show it in the diagram, but we're going to assume that these wires have a sufficient connection to where there is a current of 5 amps that's passing through this loop, right? So we've got a current of 5 amps. It actually goes through this section of wire and then passes back down. So there's a constant current of 5 amps going through this loop here. So the width of this section is 15 centimeters. Right? This is a message delivery system, so we can actually, if we run a high enough current, the magnetic and have this in a magnetic field, this will actually accelerate in the positive y direction. Right? So you can actually cause something to ascend or descend depending on how much current you pass through. So there's a 5 amp current passing through it. The length of this conductor is 15 centimeters, and the mass of the wire is 15 grams. That's good because I got the mass and the length, and I don't have to do that messy stuff I had to do here with the density or anything, right? So I've got the mass, I got to convert that to kilograms. I've got the length, convert that to meters. I've got the current. It's asking for the magnitude and the direction of the minimum magnetic field that's required to move the wire. So we're in a similar situation, but I'm not asked for the current, I'm asked for the magnetic field. But this has a mass, so it's experiencing a force due to gravity, right? And then we want the magnetic field to be pointing in the positive y direction, right? Because we want to move the wire, right? We want to move the wire, so we want it to be just large enough to overcome the force due to gravity. So I'm gonna set it up a similar way, except I have the mass and the length, which is very good. The current is 5 amps in the negative x direction. So I need the magnetic force equal to the gravitational force. Same equation, mg equals BIL, except now I'm solving for the magnetic field strength. So the magnetic field strength is mass times the acceleration due to gravity, divided out the current and the length. Okay, so I have the mass in kilograms, acceleration due to gravity, the current, and the length of the wire in meters. So a magnetic field of at least 0.2 Tesla is going to overcome, or is going to be equal, or is going to, generate a force that's equal to the gravitational force. So something over 0.2 Tesla is going to cause an acceleration in the positive y direction, and that's what we want. So what does the direction of the magnetic field have to be? Again, I'm kind of doing it backwards because I need the force to be in the positive y direction, and I know that the current is in the negative x direction now. So the current is opposite this one, right? Current is opposite our previous example. So I'm going to point my fingers in the direction of the current, but I need my thumb to be pointing in the positive y direction for the magnetic force. So my palm is facing me now. My palm is facing me in the positive z direction, so that I'm curling my fingers towards me, and that tells me the direction of the magnetic field out of the page. Positive z direction. Okay, so I'm just going to introduce this quickly before I do the example, because I think I'm getting a little close to my 45-minute mark here. So if I have a loop of wire, right, let's just say there's a part of this wire that I can open up and I can apply a voltage due to a battery, right? So I've got one single loop of wire, and I've got the current going counterclockwise. All right, current's going counterclockwise. If I have a magnetic field that's in the positive x direction, there are portions of this loop that are going to experience a force. Right? There are parts of this loop that are going to experience a force. But there are parts of the loop that aren't going to experience a force. So who does not experience a magnetic force due to this magnetic field? Those are segments 1 and 3. So you see that the current is going in the positive x direction here, negative x direction here. So if the current is parallel to the magnetic field, the cross product between I and B is 0. So sine of 0 is 0, sine of 180 is also 0. So I cross B is 0 for both of these two segments of wire. But segments 2 and 4 have currents passing through them that are perpendicular to one another. They're perpendicular to one another. But they're pointing in opposite directions. So if you want to pause the video, take a second and do I cross B for sections 2 and sections 4. Alright? Fingers in the direction of current, curl them in the direction of the magnetic field. Your thumb is pointing in the direction of the force. So if I do that for segment 2, my fingers are pointing down. I have to curl my thumb to the right. My thumb is pointing towards me. So this section of wire is actually going to experience a force out towards me. So picture that piece of wire approaching me, right? It's coming out of the computer screen. If I do the right hand rule here for section 4, my fingers are pointing up. Got to turn my hand to the right, curl my fingers to the right. It's experiencing a force into the page. So these two sections of wire are experiencing forces in the opposite direction. Right? They're experiencing forces in the opposite direction. Right? So if you think of this wire, if you got the top and the bottom not experiencing any forces, but these two sides experiencing forces in the opposite direction, and if I look at it from below, then this section of wire is not experiencing a force, but these two sections are going to cause this thing to rotate, right? So you got a force in this direction, force in this direction. If I pick the center of the loop to be my axis of rotation, the loop is actually going to rotate inside this magnetic field. Now it's going to get to a point where these forces are going to cancel out, right? Once this thing rotates 90 degrees, it's actually not going to experience a force. So we're just concerned with the force right now when the loop is in the B field like this, right? But it is going to start rotating, and the force on these two segments is going to decrease because the angle between the current and the magnetic field are going to change. So eventually this is going to come back to equilibrium, but it's going to be vertical. So we're concerned with the torque that is being exerted on it the moment it starts to rotate. So I have a derivation. It looks crazy right now, but I'll kind of walk us through this derivation. So if these two forces are being exerted on the piece of wire, and this thing is rotating, then these two forces are actually generating a torque, right? So torque was a cross product, if you remember, from 120. I also have those notes uploaded from 120 if you need a refresher. The torque is the cross product between the radius vector, so that's the distance from the axis of rotation to where the force is being applied, and the force vector at that location. So it's R cross F for this force, and it's R cross F for this force. So I did this for a rectangular loop, right? So that's A and that's B. Maybe it'll be, I think my example, we do a square loop, right? So that's going to be A, that's going to be A, they're going to be the same side. But this length of wire is a length B. So the distance between where the forces are being applied and the axis of rotation is B over 2. Now at this moment, the radius vector and the force vector are perpendicular. So we don't have to worry about the sine theta from the cross product stuff. So the torque at this moment, right? So the torque at this moment is the force on the piece of wire times the distance between that where that force is being applied and the axis of rotation. Okay, so I'm adding up these two torques, right? Let's say from this location, they're both causing torques in the same direction. They're both causing it to rotate clockwise from this point of view. So it's just the sum of those two forces times B over 2, right? Their respective radius vectors. All right. The force F2 and F4, they are the force on a current carrying wire due to a magnetic field. So it's BIL. Capital B, the magnetic field strength, I is the current, A is the length of wire that's inside the magnetic field. So I'm using A as the length of wire inside the field that's experiencing the force. So it's the same for F2 and F4. It's the same current going through the loop. It's the same magnetic field. They're both the same length. So F2 and F4 are the same. The magnitudes are the same. IAB, IAB. So if I add these two together, I get the current times the magnetic field times the area that the loop makes. Right? This is a rectangular loop. So the area is the length times the width, A times B. So what happens is once it starts to move, right, the angle between the force vector and the radius vector changes. So R cross F changes, okay? And so what's happening is the torque is going to eventually get to 0, right? So the max torque is when the loop looks like this. But as the loop starts to rotate, the angle between the radius vector and the force vector changes, so the torque is changing. Okay. And so now we have to account for that sine theta component for each one. B2 sine theta, B over 2 sine theta, B over 2 sine theta. The derivation is very similar. We just have those sine terms with it to account for the change in direction of the vectors. Okay. So this angle is actually this angle right here, and we'll talk about this vector here for a second. So I've got the current, I've got the magnetic field. I still want to be able to do a cross product, right? I still want to do a cross product like I did with torque, right? Because it's R cross F. So I still have the same term, right? A cross B, right? But I want a vector, right? I want a vector quantity that I can cross product with the magnetic field to get the direction of the torque. And that vector is my area vector. Right now you're saying area is a scalar, it's not a vector component, it doesn't have a direction. And we'll talk about this more in chapter 20 when we talk about flux. If I take this surface of the area enclosed by the loop, and if I draw a vector perpendicular to it, that's my area vector. That's my area vector. Okay, so if I do the right hand rule for torque, if I point my fingers in the direction of A, curl them in the direction of B, my thumb is going into the page. Okay, and if you go back to 120, my thumb's going into the page. That's going to cause a clockwise rotation of this object, right? And that's what we see here, right? F4 is pulling it down this way, F2 is pulling it up this way, so I have a clockwise torque. So I want to use the area vector A cross B to help me determine the direction that this loop is going to rotate. Okay, so this is my formula for the torque on a loop of wire in a magnetic field if the wire is parallel to the magnetic field and we're looking for the instantaneous torque as soon as it starts to rotate. I can drop the sine theta and just use this expression right here. Alright, so I'm going to pause the video. I've got this loop here. I'll do this example at the beginning of video 3, and we'll see some I have some diagrams up, and we'll talk about how we figure out the angle between that area vector that we just talked about, A, and that magnetic field vector. Okay, and I'll start that with the beginning of video 3. Thanks. See ya.